Okay guys, so in this video we're going to talk about curves defined by parametric equations because eventually we want to be able to do calculus with these parametric equations, but many of you have probably had very little or no experience with parametric equations in the first place, so we need to define them. Alright, so basically imagine we have some particle that moves along the curve shown in the direction shown as well. So basically as time goes on, it moves in x and y. So it goes up or down and left and right. So essentially, it's not really possible to describe the function in some form y equals f of x. This is actually describing something that absolutely would not be an explicit equation, that is, y equals something in terms of x. At best, it would be implicit, so you'd have like x's and y's equal something. So we basically would struggle to solve for y equals something. And because of that, it's often actually really hard to describe this thing in terms of x and y as a single equation. And so, but since x and y are both functions of time, we can write x equal to some function of time and y equal to some function of time and use these to describe our curve. So rather than thinking about it in like a single equation, we're basically thinking about it as two equations depending on the same like variable. All right, and technically speaking, this isn't actually limited to just like two-dimensional space, but we're only going to focus on two-dimensional space. Now, technically speaking, we've actually seen this sort of in the past. We'll talk about that. So first we need to talk about parameters. So if both x and y are functions in a third variable t called a parameter, it could be any variable, but we generally use t, then we say that x equals f of t, y equals f of t are parametric equations. So we have x solved for something in terms of t and y is solved in terms of t. And as t varies, then both x and y also vary and trace a curve called a parametric curve. And as mentioned, first of all, we can do this with more than just x and y. We could do z and so on and so forth. But we've actually already seen this. If you remember from your solving systems of linear equations, when you have infinitely many solutions, we want to write this in terms of either z's or t's. I generally write it in z's, but you'll see it sometimes also written in terms of t, and that's because they are actually writing them as a parametric equation. So if we have some system here, let's go ahead and solve it real quick. We'll go to Desmos matrix. We're going to create a new matrix. It's going to be a 3 by 4, and we'll go ahead and plug this in. So we have 1, -1, oops. We'll type it in the correct place. 1, -1, 5, -2. We'll have 2, 1, 4, 2, 2, 4, -2, and 8. Okay, so if we do reduce row epsilon on this thing, we will get this matrix, which is essentially equal to, well, it is equal to x plus 3z equals 0. We have y minus 2z equals 2, and we have a bottom row 0 is 0, which is a true statement, which if we remember from algebra, that's how we learn to recognize infinitely many if we solve them with reduced row epsilon. Okay, so if we look at this thing, basically we have two equations in terms of z. So if we solve for x, we get x equals, so we'll move that 3z over, minus 3z, so that's what x equals. And we have y equals 2z plus 2, so we added 2z over to the other side. So essentially what we have is we have x in terms of another variable and y in terms of that same variable. These two things are parametric equations. They are defined in terms of some other variable. And so what we did then is we said something like, okay, well, the solution is -3z, 2z plus 2, so this is your x, this is your y, and then you'd say z. Because that's what z is. Z is obviously z. So we'd say z. So basically, these two things are dependent on what z is. So when z is 1, or 0, or 2, it changes. So for example, when z is 0, then the point would be 0 to 0. That would be one solution, or I should say one point where we would be when z is 0. If we had like z is 1, then we'd have negative 3, and we'd have 4, like that. So we'd have the next point when z is 1. Now, this is also why we often, well, I don't do it personally when given the choice, but you'll see it oftentimes in like homework systems, is that they want z in terms of t. So they'd basically say, okay, z equals t, and then that means then that y equals 2t plus 2, and x would be negative 3t. So we have x and y in this parametric equation form where we're used to seeing them as t's. So these are parametrics. And so that's what we're going to be doing with writing our kind of equations in parametric form. And the reason why we do that is because in a lot of situations it's actually a lot easier to describe them in these ways than in terms of x's and y's, and thus it's going to be a lot easier to do calculus in those terms than it is to do it in terms of x and y. We could always maybe convert them back into x and y if we could maybe solve for like t equals something, but sometimes that's even on its own very, very challenging. Okay, so let's take a look at some examples. So sketch the curve by using the parametric equations to plot points and indicate the direction at which the curve is traced as t increases. Eliminate the parameter to find a Cartesian equation of the curve. So basically, let's start with how this thing here is solved. X is t squared minus 3, y is t plus 3, or t plus 2, and t is between negative 3 and 3. All right, so essentially, if we think about this, our first point, t is negative 3. So when t is negative 3, our x and y we end up with is going to be some ordered pair, and we plug negative 3 in for t into both of them. So x equals negative 3 squared minus 3, and y is negative 3 plus 2. So that means when t is negative 3, our very first point would be 9 minus 3, which is 6, negative 1. So that would be our first point. Then our next point would be when t is, say, negative 2. So when t is negative 2, we would do, all right, x equals negative 2 squared minus 3, and y would be negative 2 plus 2. So our next value would be 4 minus 3, which is 1, 0. So that would be our next point. And so we could start graphing this on Desmos here. So we have a point, 6, negative 1. Okay, that's our first point. Our next point, in whole number form at least, would be 1, 0. Okay, so it's going backwards essentially here. Then we could continue in this fashion. I think it will be easier if we describe it as a table, so let's go ahead and do that. So let's call this like f of x, and we'll call the next one our y as like g of x, just to make my life easier. So f of x is our x squared minus 3. I'm going to hide that. And our g of x is going to be the other equation in terms of x here, x plus 2. Hiding that. So basically, when we're talking about this thing here, let's go ahead and say x, f of x, and g of x. Okay. So essentially, when x was negative 3, we got 6, negative 1. Okay, that was our first point there. 6, negative 1, which again was there. Then at negative 2, we had 1, 0 right there. Then when t was negative 1, we get another point, negative 2, 1. So let's go ahead and graph that. Negative 2, 1. Okay, so that's our next point. Then when x is 0, we have the next point, negative 3, 2. So let's go ahead and put that. Negative 3, 2. Okay. And then we have 1, 2, and 3, and they continue in that fashion. Now, we can also graph this thing as a parametric. We could continue in this fashion. I might as well. So let's see. We had negative 2, 3, negative 2, 3. That was our next one. Notice this is definitely not a function. Let's just cross through here. We have 1, 4. Okay, there. And then we have our 6, 5. 0.65. Okay, so let's go ahead and label this. This is when t is 3. This is when t was 2, 1, 0, -1, -2, and -3. So basically, we can trace this curve along here. Now, we can also graph this in terms of parametric. So what we do is as an ordered pair, we would say something like in our x position, this is t squared minus 3, comma, and then we have our t plus 2. Okay, and we want to set this between -3 and 3. Okay, so this is what our function, or non-function, this is what our equation looks like. It's basically a parabola but set on its side. So it's not a function, but rather than trying to write this thing in terms of x's and y's, it's just easier to write it as a parametric. Now, a few things to note about this as well is it's important to pay attention to what these values are at the different times. So again, we have this thing here, and this curve is not just like left to right, it's actually starting here and going this way. So this shows the direction that it goes, because when we have like normal, these are terrible arrows, sorry, but when we have normal kind of like functions, they go from left to right in terms of x. But here we're talking about t, and so in this case, if you notice, at the start of our time, we were going to the left, and then we were going to the right. Okay. So this is our curve that is being described here, and this is the complete curve because it's only from time is -3 to 3. Okay, now let's talk about what this would look like if we were talking about it in terms of a Cartesian. So again, x equals t squared plus 2, I believe, or maybe -2, -3. Okay, the other one was the plus 2. -3, so y equals t plus 2. So if we wanted to describe this thing in terms of a x and y, that is doable. We just need to solve for t for one of these. I think it would be easier to solve for it in this one. So I'm going to subtract 2 over, so -2, and we get y minus 2 equals t. So now we're going to plug our y minus 2 into this equation here, and we get x equals y minus 2 squared minus 3. So that is to say, if we clean this up, first of all, we actually don't really like it in terms of like our just like x equals. That's not really very explicit. We'd like to solve it for y. Now, to do that, then I'm going to move that 3 over, so plus 3. And we get x plus 3 equals y minus 2 squared. And then we're going to take the square root of it. So when we take this square root, when we personally write this square root, we need our plus and minus. So basically, we end up with, I'm going to write this on the other side, y minus 2 is equal to positive square root x plus 3, and y minus 2 is equal to negative square root x plus 3. Okay, so that means if we add 2 to both sides, we get y equals the square root of x plus 3 plus 2. And over here, y equals, I'm going to write it first, 2 minus the square root x plus 3. And technically, I probably should have written the first one here. But the point is that we need two equations to describe this in terms of y equals, because of that square root, basically. So let's go ahead and graph this. This one is going to be the upper side, and the other one's the bottom side. But let's go ahead and see it. Y equals the square root x plus 3 plus 2. So there that is, but notice it goes on forever. And the other one, y equals negative square root x plus 3 plus 2. And that's the bottom side. So again, we could describe it, but notice we'd still need two equations to do so. So no real need to, well, so essentially it's better to write it in this parametric form. Okay, also then we can also tell like which direction our curve is going and what path our, if we think about it as some particle with respect to time, what path our particle is taking. Okay, let's take a look at another one. Okay, so same directions as before, we're going to sketch the curve, and then we're going to indicate the direction, and we are going to write it as a Cartesian equation. So let's start with essentially, again, a table. So it's often easiest to think about these things in terms of a table. So if we do t, right? T, we have our x, which is 3 sine t, and we have our y, which is going to be 6 minus 3 cosine t. Okay, so when we're gonna start at time is 0. So when time is 0, then sine of 0 is 0 times 3 is just 0. So we have 0. When cosine of 0 is 1 times 3 is 3. 6 minus 3 is 3. So that's our first point. Now let's go ahead and go to pi halves. Sine of pi halves is 1 times 3. That would be 3. Cosine of pi halves is 0, so that would be 6. Let's do the next one. Let's say pi. Okay, sine of pi is 0. Cosine of pi is negative 1 times negative 3 is positive 3 plus 6 is 9. Alrighty, we'll extend this further out. Our next point for time would be 3 pi halves. So that is sine of 3 pi halves is negative 1. 3 times negative 1 is negative 3. We have cosine, that would be 0 and 6. And then our last one is 2 pi. Now 2 pi is going to be the same thing, 0 and 3. Okay, so we can tell, hopefully, we can probably tell that this is probably going to be a circle of some sort. It's just kind of shifted around. And if we go to graph this thing on Desmos, we have 3 sine t, comma 6 minus 3 cosine t. Okay, and it's from 0 to 2 pi. All right, we can definitely see our circle here, and we have our points around here. Now let's think about what we're doing here as far as which direction. So our first point was 0, 3. Then the next point was 3, 6. So essentially what's happening is we have our parametric is starting here and circling around until it comes back. That's what happens. So it's kind of going counterclockwise. All right, now let's talk about how we can now write this thing in terms of Cartesian. So first of all, what we need to do in order to do that is think about our Pythagorean identity. Sine squared theta plus cosine squared theta is 1. So we're going to use that logic, and we're going to solve for sine here. So if we solve for sine in our x equals 3 sine t. And we'll also do that for y. So y equals 6 minus 3 cosine t. So essentially what we want to do is we want to solve for sine. So if we divide by 3 on both sides, we get sine of t is equal to x over 3. Okay, we'll do the same thing with cosine here. We're going to add that over. We get 3 cosine t plus y equals 6. And then we're going to solve for our cosine by subtracting our y. We get 3 cosine t is equal to 6 minus y. And our last step here to get cosine by itself is to divide by 3. Cosine t is equal to 6, well, 6 over 3. I might as well write that. That's 2 minus y over 3, which we could write this as our 6 minus y over 3 if we wanted. Either way. Now, there's some benefits to writing it in this form, as we'll see. Now, we know that sine squared plus cosine squared is going to be 1. So all we need to do is square both of these things. And we end up with x over 3 squared plus cosine squared, which would be our 6 minus y over 3 squared, the better form for this, squared, is equal to 1. So we have our equation right here. We have the in Cartesian. Now, there's no way to write this as implicit, or excuse me, as explicit, so implicit will do just fine. And to be honest, we generally write our circles in this form, so it's honestly better anyway. So we get x squared over 9 plus we have 6 minus y squared over 9 equals 1 right here. Now, if you think about it, we generally would write this by multiplying that 9 off the bottom. So this is x squared over 9 plus 6 minus y squared over 9 equals 1. And with circles, we usually put that 9 onto the other side. So multiplying by 9, we get x squared plus 6 minus y squared equals 9. And the reason why we generally do that, because again, our general equation is like x squared plus y squared equals r squared. And that is kind of a normal form. We'll sometimes write this as like x plus or minus some a or something squared plus y plus or minus some b squared equals r squared to adjust. So it like this would be the horizontal motion and y would be the vertical motion here. So if you notice, moving this thing up, we moved the 6 here, we moved it up to here, 6. Okay, now I don't really know if this is kind of like off the top of my head, if it's like minus a or minus b, whatever, doesn't matter. But the point here is that we have this thing, and this tells us that we have a vertical shift up, a 6, and we have a radius here of 3. Okay, so there is our equation in Cartesian. And again, this is okay, I suppose. I mean, we could do this derivative with implicit, but yeah, it might not be necessarily the best move in all situations with calculus. All right, let's try another one. So again, sketch this curve by using our parametric equations to plot it, indicate the direction of the curve, and then eliminate the parameter, find Cartesian equation. Okay, so again, we'll create a table, T. We have our x, which is equal to 3 cosine t, and we have our y, which is equal to 4 sine t. Okay, so when time is 0, that's our first time here, then cosine of 0 is going to be 1 times 3 is 3. Sine of 0 is 0, so that's 0. Okay, so now we'll go ahead and do like pi halves. All right, so at pi halves, cosine of pi halves is going to be 0. Sine of our pi halves is going to be 1 times 4 is 4. Okay, and then we'll go ahead and do pi. Now with pi, I'll write it in the same color as the rest of them. So cosine of pi is going to be negative 1 times 3 is negative 3. Sine of pi is 0, so it's here. So what is this thing here describing? Well, it sounds like potentially some kind of ellipse. Let's go ahead and see it. Okay, so we have 3 cosine t, comma 4 sine t, and t is between 0 and pi. Yeah, it's the top of an ellipse. So our first point here was 3, 0. And so we're here and we're going in that direction. So again, if we want to show this thing, we would show the direction by drawing arrows. Okay, so it's an egg shape. So it's the upper half of a ellipse. I was going to say elliptical. All right, so let's now talk about how we could solve this thing and write this thing in terms of a Cartesian form. So in this case, same thing as before. We know that cosine squared t or plus sine squared t is going to be equal to 1. So essentially, we're going to kind of get those things on their own again. So that is to say x equals 3 cosine t, y equals 4 sine t, and we are going to solve for cosine and sine. So divide by 3, divide by 4. We get x over 3 is equal to cosine t, and y over 4 is equal to sine t. And so if we square those things, we end up with our x over 3 squared plus y over 4 squared is equal to 1. Again, sine squared, cosine squared, 1. In this case, I did cosine squared plus sine squared equals 1, but same thing. All right, again, coming from squaring both sides here. Now, in this case, this is actually a more normal form for our ellipse. We are talking about leaving this bottom alone because it tells us kind of how wide this thing is and how high this egg is. So y over 4 squared equals 1, something like this. So notice this is our upper half of our egg, and our egg has a radius, well, has a width here of 3 by 3, so it's like kind of a total distance of 6 across and 8 tall. Okay, so we have our egg. All right. So now let's talk one more thing I want to at least bring up. I'm not going to go too much in depth with it, but it's a really common thing when we talk about parametric curves, and that is called the cycloid. There's actually a lot of pretty cool applications of the cycloid. If you kind of Google it, you'll get some pretty interesting stuff. But essentially, a cycloid is the curve traced out by a point P on the circumference of a circle as the circle rolls along a straight line. That's what a cycloid is. So essentially, if you think about like a nail stuck in your tire, it's the motion of that nail as the tire rotates. And so this right here, this point P, as it's being rotated along the straight line, kind of like the road, that point, as it shifts to the right, is kind of following this curve and doing that. And so these cycloids have some pretty interesting applications to them. I think one of the ones that I find pretty interesting is the fact that the cycloid was kind of thought to be used as potentially like a pendulum for like a grandfather clock style things, to make sure that essentially no matter how wide the pendulum swing was, it took the same amount of time. There's also a lot of cool applications of the cycloid when we talk about like balls rolling down a cycloid-shaped curve. So there's some cool stuff with that as well. But essentially, parametric equations of the cycloid are of the form x equals r times theta minus sine theta, and y is equal to r times 1 minus cosine theta, which if you notice, that's parametric. So, polar. So this, well, it's parametric and polar. So it's describing our x's and y's in polar equations, r's and thetas. And so we can also do that, and you'll see that later when we talk about our polar calculus, where we define something polar but also parametrically. So anyway, that's good enough for kind of the cycloid. I just want to bring it up because I would be remiss not to mention it, but we just don't have time to go into some of the more interesting to me aspects of the cycloid. So like I said, Google cycloid and watch some videos on YouTube maybe. Anyway, so that is our curves defined by parametric equations, and the idea here is that, again, there are times when it would be easier to define our curve in terms of parametric and then do calculus with it rather than trying to do calculus of these really complicated equations that aren't actually functions and then trying to do calculus with those. It's not all that great. I mean, it's doable, but it's actually much easier in terms of parametric. So that's the idea. And so in our next topic, we're going to talk about actually doing the calculus with the parametric. Anyway, thanks for watching.